What we're going to be talking about today is common negative feedback amplifier topologies. And these are the most commonly used op-amp circuits in practice. So these are the types of circuits that are used to accomplish a specific function or mathematical operation using an op-amp, okay? So the first one that we're going to look at, and we'll give it a name in a minute, is something that we've actually already looked at. It was the last problem that we worked on Monday. So let's call this the inverter. Over here is our output terminal. And so let's consider a system where we have some feedback resistance, RF, like so. Some resistance R1. We're going to apply some input voltage at that leg of R1, and our non-inverting input terminal is grounded, and we're trying to determine the relationship between our input voltage and our output voltage. So I'm going to use the three-step process that we developed on Monday, but I'm not going to write down all three steps over and over and over again because I am tired of it, and you guys probably are too. So applying our first step, we know that this current is 0 amps. This current is 0 amps. And our voltage present at our non-inverting input terminal must be 0 volts because the non-inverting input terminal is connected directly to ground. Moving on to step 2, we know that the voltage present at our inverting input terminal must be the same as the voltage at our non-inverting input terminal. And now we are going to write a Kirchhoff's current law equation where we add this guy and this guy together. So that KCL equation is going to look like 0 minus Vn, so negative Vn over R1, plus 0 minus V out, so minus V out over RF is equal to 0. And with a small amount of algebra, we find that our output voltage is negative RF over R1 times our input voltage. So this is what's called a negative, that's not right, an inverting op-amp, or an inverting amplifier, okay? It's an inverting amplifier because if we apply a positive input voltage, we get out a negative output signal. So it inverts the polarity of the applied signal. It also applies some voltage gain. So our voltage gain, AV, will be by definition the ratio of the output voltage to the input voltage of our amplifier system. And in this case, that is simply negative RF, over R1. So if we have an amplifier circuit with this particular topology, we no longer need to analyze anything. We can say that the output voltage is simply negative R2 over R1 times whatever we have at our input, with no circuit analysis whatsoever. This type of circuit will always work this way. So the ratio of resistances RF over R1 can be either used to scale or make larger the input signal, right? So it can amplify things. It can also be used to attenuate signals or make them appear smaller at the output. So we get two different types of functionality, both amplification and attenuation. The trade-off here is that the polarity of our output signal will always be opposite to the polarity of our input signal. Right. Now let's look at our second configuration. And this is similar to something that I had you guys do in the in-class assignment. So this is going to look almost exactly the same. There is one key difference between these two circuits. I'm mentioning this to you guys because in your lab today, you're going to be asked to build these two circuits specifically. And if you set things up correctly, changing between the two circuits is literally moving two wires. So for this particular circuit, we are going to ground the terminal of R1 where we had just placed our input voltage. And we are going to apply our input voltage at the pin that we had previously grounded. So we're literally just, if you swap these two voltages, VN and ground, in this configuration, you have what I'm going to call a non-inverting amplifier in a moment. We'll see why. You switch them back the other way, we have an inverting amplifier. Okay. So from here, we know that these two currents are 0. And obviously, the voltage present at our non-inverting input terminal is simply VN, which means the voltage present at our inverting input terminal is also VN. Now, writing our Kirchhoff's current law equation, adding the two currents that I've indicated together, we are going to have VN minus 0 over R1. So that looks like VN over R1. And our current directed up to the feedback resistor is going to look like, VN minus V out. Over RF is equal to 0. And with a little bit of algebra, we find that V out will be equal to 1 plus RF over R1 times VN, which means our voltage gain for this particular configuration, again, voltage gain is nothing more than the ratio of the output voltage to the input voltage, is 1 plus RF over R1. So this is the non-inverting amplifier. And in a non-inverting amplifier, if we apply a positive input voltage, we get a positive output voltage. So it does not invert the polarities. Another way that you can tell the difference between these two circuits is the non-inverting amplifier has the input voltage applied at the non-inverting input terminal, and the inverting amplifier has the input voltage applied through a resistive network at the inverting input terminal, right? So if the voltage, applied voltage is on the non-inverting side, chances are you've got a non-inverting amplifier, and if it's on the inverting side, you've got an inverting amplifier. Okay. So this non-inverting amplifier, it can only amplify signals, right? So the smallest possible output signal we could get is just the input signal itself, because we're always going to have 1 plus the ratio of resistances. So if R1 is much larger than RF, we get what's called a buffer amplifier. Whatever you get in is equal to, or excuse me, whatever you put in is equal to what you get out. You might be asking yourself, why would you ever want to have an amplifier with a gain of 1? Well, buffer amplifiers are used when you want to make sure that your system has a very high input impedance. So effectively, you're using the op amp's high input resistance itself to enhance the performance of your circuit. Okay, so it is something that's done in practice very, very often. All right. So let's look at our third configuration. So this circuit is going to look incredibly similar to our inverting amplifier, but there's going to be a subtle change. Let me make this a little slightly larger here. So here we have our feedback resistance, RF. I'm going to ground my non-inverting input terminal. And then over here, I'm going to connect multiple resistors. So let's call this one R1, this one R2, this one R3. And I'm also going to apply multiple input voltages. So let's call this V1, V2, and V3. And over here, we have V out. So applying op amp rule number 1, we know that no current flows into or out of our input terminals. And our voltage at our non-inverting input terminal is 0 volts, which means the voltage at our inverting input terminal is also 0 volts. Applying Kirchhoff's current law at our at our inverting input node, we're going to add those 4 currents together. And in this case, that's going to look like 0 minus V1, so negative V1 over R1, plus 0 minus V2 over R2, so minus V2 over R2. Similarly, minus V3 over R3, plus 0 minus V out, so negative V out over RF is equal to 0. And rearranging, we find that our output voltage is negative RF times V1 over R1 plus V2 over R2 plus V3 over R3. We can't really define a voltage gain for this system because we don't have a single input voltage that we're dealing with, okay? What this amplifier is called is it's the weighted inverting summer. So it adds together the input voltages to create the output voltage. And each of the input voltages is scaled by a different amount. So it's a weighted addition, okay? Now, if R1, R2, and R3 were all the same thing, our output voltage would simply be negative RF over R1 times V1 plus V2 plus V3. And we now have an inverting summer. So we no longer scale each individual input signal by its own amount. They're all scaled by the same thing. So this is the first obvious instance of analog signal processing, okay? We can use an op amp to literally add signals together, okay? So where do you think something like this might be used? How many of you have ever driven across state lines and seen a way station? Pretty much everybody, right? So the load cells that you drive the trucks on top of create a small amount of voltage depending on how heavy the thing that's sitting on top of it is. If you have multiple load cells connected in a string, and then you want to add the output signals of all of them together to find out the total weight of a truck, this is literally the circuit that does it. This is also the same circuit that's used in your common electronic or digital bathroom scales and all of that kind of good stuff. If you ever want to add a bunch of signals together, this is how it's done, okay? All right, let's move along to circuit number 4. So we just did addition with op amps, so now we're going to do subtraction. So this circuit here is effectively both an inverting amplifier and a non-inverting amplifier at the same time. In fact, we could analyze it using superposition using those two things, okay? So let's say that we have some feedback resistance R, and we have a resistance R here connected between the inverting input terminal and our voltage V1. And then on this side, we have another resistor R connected between our non-inverting input terminal and our voltage V2. And then finally, we are going to have a fourth resistance R here between our non-inverting input terminal and ground. Now it is critical that all of these resistors are the same thing. Okay. It's not going to break the circuit or anything like that if they have different resistors, but the math is not going to be pretty unless all of these resistors are matched. Okay. So applying op amp rule number 1, we know that both of those currents are 0. And we now need to figure out what the voltage at the non-inverting input terminal is. Does anybody have any thoughts? Okay, so what voltage does that give me? 1/2 V2, absolutely right. So effectively, all we have connected to our non-inverting input terminal here is a simple voltage divider, because we know that none of the current can branch off and flow through into the input terminal. And because our resistors are the same, the voltage just gets divided in half. So V plus is just 1/2 V2. That only works if the resistors are equal. So we know that our voltage V minus must also be 1/2 V2. And now we can write a Kirchhoff's current law equation like we have done so many times before. So we're going to have 1/2 V2 minus V1 over R plus 1/2 V2 minus V out over R is equal to 0. So that's my KCL equation, right? So if I were to multiply both sides of this equation by R, I would just get rid of that denominator, right? So I could say that 1/2 V1 minus V1 plus 1/2 V2 minus V out is equal to 0. So all I'm going to do now is I'm just going to move V out to its own side of the equal sign. And on the other side, we have 1/2 V2 plus 1/2 V2, which is just V2 minus V1 is equal to V out. So this gives us the difference between analog signals. Okay. So we've performed addition, we've added signals together and scaled them by some amount. This one allows us to take the difference between signals. Okay. Now, if we happened to use different values of resistors, so not all of them were the same, we would still have something similar to this. It would be some scaled portion of V2 minus some scaled portion of V1, but the math is not pretty at all. So I would argue that if you wanted to do some type of scaled subtraction, your best bet would be to do a two-stage or multi-stage amplifier where the subtraction takes place just doing something like this, and then you could either scale your input signals or scale the overall output by feeding this as the input into another stage. Okay. The math behind weighted differencing is just wildly annoying. It's much easier to just use two circuits to do it. So this is our differencing amplifier. Right. So far with op amps, we have done amplification, so making signals bigger, so scaling by a factor greater than 1. We have done attenuation, scaling by a factor less than 1. We have done addition, and we have done subtraction. Multiplication and division can't be done with a single op amp, so we're not going to deal with those, but differentiation and integration can be done with a single op amp. Yeah, no, it's really interesting. So differentiation and integration. So effectively, think about it in this way, okay? Let's say that we had a voltage waveform. And it was a series of triangular pulses like this. Right? Actually, let's change this slightly because that's going to give us impulse functions that I don't want. Let's do a sawtooth wave like this. What would happen if we took the derivative of this wave? What would it look like? The slope is constant, right? So let's call this dV by dt. Positive slope gives us a positive DC voltage. negative slope gives us a negative DC voltage back and forth like so. So being able to take the derivative of a triangular wave is how we get square waves or vice versa. Right? So taking the derivatives of signals is actually something that's done very, very regularly in signal processing. It's also part of control schemes, part of communication schemes, as it turns out. Being able to take a derivative of a function is a low pass filter. Being able to take the integral of a function is a high pass filter.
Okay, so I guess follow-up question is like, so like any analog 80s sort of goofball sim is going to operate on some kind of principle like this.
Absolutely.
With a triangle wave, square wave is going to take
Yeah. And there's another op-amp circuit called a comparator that can convert sinusoidal waves into square waves. But that's an open loop op-amp circuit. And since we're talking about negative feedback op-amp circuits, we're not going to do that. But yes, so you can convert a sinusoidal input into a square wave, into a triangle wave. And yep, so that's how analog synthesizers and all that kind of stuff work. So, all right, so our fifth circuit is going to be this guy. So we start with our simple op amp. And what we are going to do here, so the slight problem I have here is I can never remember which one is which. So let's start with this one. We're going to put a resistor in the feedback position. We are going to ground our non-inverting input terminal, and we are going to put a capacitor C between our non-inverting input terminal and our input voltage. So because we have a capacitor in here, I'm going to remind you guys of our capacitor voltage and current relationships. So the current through a capacitor, IC T is equal to C dV by dt. And the voltage drop across the capacitor is 1 over, sorry, let me save this and restart this program, or it's going to keep giving me that annoying error. I'm using the integral form that starts at negative infinity instead of starting at T naught, so that we don't have to care about initial conditions and things like that. It's just going to make the math easier for us here. Okay. All right. So I'm going to call this voltage the voltage drop across the capacitor, and this current, the current flowing through the capacitor. Okay. So for the most part, we're still going to do the same 3-step process, but we're going to have to get a little bit creative here. All right. So this current is 0 amps. This current is 0 amps, which means, actually, that's not what this means. But next we can say that this voltage is 0 volts, which in turn means that this voltage is also 0 volts, right? So now I'm going to write a KCL equation, but I'm going to write it slightly differently. I guess it wouldn't matter, but I'm gonna write it this way anyways. So I'm gonna say that the current flowing in is equal to the current flowing out, just so that I don't have to mess around with negative signs here. Okay. So the current flowing in is obviously IC, and the current flowing out is 0 minus V out over R. Okay. Well, IC is C dVC by dt. So this will be negative V out over T. So my goal here is to relate my input voltage, bless you, to my output voltage. So how does my input voltage relate to my capacitor voltage in this case? So Vn is the voltage drop across the capacitor. Absolutely right. Right, because Vn is a voltage measured between that input terminal and ground, and the capacitor voltage is between the input terminal and a virtual ground, because our non-inverting input terminal is grounded, right? So because this voltage is 0, this is effectively also a ground. Vn and Vc are the same quantity. So rearranging, what we will find is that V out will be equal to negative RC times the derivative of VC, which is the same as negative RC times the derivative of our input voltage with respect to time. So this is a differentiator or differentiating amplifier. Okay? It takes the derivative of our analog input signal and then also scales it by some amount. We could also realize this circuit using an inductor, but the inductor would have to be in the feedback position because the current and voltage relationships are inverse, so the position of the elements has to be inversed as well.
So what is, if you have that circuit, changing the value of the capacitor is changing the magnitude?
Yeah.
And the resistors doing the same?
Yes, but so one thing that you do have to pay attention to here, and it's not a coincidence that we effectively have the time constant of an RC circuit in this thing, is it takes time for the capacitor to charge and discharge, which we didn't get to physically see because we didn't get to do the labs and all that kind of stuff associated with that, right? So we have to make sure that the values of R and C here also satisfy the constraints that we're allowing the capacitor enough time to charge or fully discharge, depending on the frequency of our input signal, right? So if the frequency of our input signal is too fast, so it's changing too quickly, our capacitor never charges and fully discharges. So instead of going from a nice square wave, it's just going to step up a little bit over time.
So, regardless of your CNR levels, the frequency of your input voltage is not.
Right, the input voltage is whatever we're using to excite the circuit, yes. All right, so this was the differentiating amplifier or the differentiator. So now we're going to simply switch the position of the resistor and the capacitor, and voila, we will have an integrator. So our last circuit of interest is this guy. And to refresh you guys, we have these capacitor relationships. All right, so let's say that our capacitor voltage do it in purple, is this voltage, and our capacitor current is in turn this current. So applying op-amp rule number 1, we know these currents are 0. By inspection, the voltage present at our non-inverting input terminal is 0, which means the voltage present at our inverting input terminal is also 0. This current will be equal to this current. So my current flowing from left to right through resistor R is Vn minus 0 over R. And my current flowing out is IC of t. Well, IC of t can be expressed as 1 over c times the integral from negative infinity yeah, actually, hold on. Yeah, I'm just using the wrong relationship. So, okay. All right, so my apologies there for that mistake, a little bit of a brain fart. So this is our KCL equation. This is perfectly fine. Now, the problem here is that we need to relate this input voltage to our output voltage, right? We know that our current flowing through our capacitor is related to the voltage drop across the capacitor by one of these expressions. So my question to you guys is, how is the voltage drop across the capacitor related to the output voltage of our system? So I would argue that V out, which is the voltage measured from this node to ground, is negative VC. Because VC is measured between ground and the output node, okay? So if we can say that V out is equal to negative VC of t, then we're going to have negative 1 over c times the integral from negative infinity to t of I of c t prime dt prime. Since I of c is in turn related to our input voltage, this is going to look like negative 1 over c times the integral from negative infinity to t of Vn t prime over R. And finally, since the resistor value is a constant, we have this relationship. Our output voltage is negative 1 over RC times the integral of our input voltage. So this is an integrator.